In this video, we're going to explore different types of chemical reactions. So again, just to review, the reactants are on the left side of an equation, the products are on the right side. Reactants are the ingredients you start off with, and the products are the things that you produce. And during a chemical reaction, the products are new substances. They have a new chemical identity. So in chemical reactions, you can find many different types. There are 5 types that we'll explore in grade 10, and you'll actually also re-explore these in grade 11 in some more detail. In this video, we're going to explore synthesis reactions, decomposition reactions, and 2 types of combustion reactions, complete combustion and incomplete combustion. In the next videos, we're going to see single and double displacement reactions. So a synthesis reaction basically just means 2 things coming together to make one. So here you have chemical A, chemical B. They react to make one thing. AB. It's one thing connected together there. And so as long as you see 2 things coming together to make one, then you have a synthesis reaction. So for example, you might have H2 plus O2 produces H2O. So this was chemical A, this is chemical B, and they produced chemical AB. 2 things made one. Very straightforward. You need to be able to identify a reaction as being a synthesis. When you see 2 things, or more than 2 things, it could be 3 things coming together to make one thing, then you know it was a synthesis reaction. You can also predict some products, and I'm going to teach you a few. You don't have to know how to predict every single one, but there are some that I will want you to know how to do, and I'll circle those ones and let you know along the way. So suppose we saw this example here, a metal reacting with oxygen. If a metal were to react with oxygen, for example magnesium reacting with O2, you could predict the product by simply doing the crisscross between the metal and oxygen. So to figure out that magnesium oxide would be the product here, I simply did Mg plus 2 because it's in group 2, O2 minus because it's in group 16, needs to gain 2 electrons. Crisscross it, reduce it, or charge balance it, and you get MgO. You can do the same thing for this one here. Here you have 2 things, so Na is the metal plus oxygen. We can predict that that would give us Na plus 1, O minus 2, crisscross it, and you get Na2O. Keep in mind right now I'm not balancing equations. I could ask you to balance the equation as well as predict the product, but right now I'm just showing you what the product is, and then you could balance later on. Okay, so this was an example of a synthesis because 2 things came together to make one thing. You can probably try predicting the product for Ca plus O2. I'll put the answer down. First try it yourself, so pause the video, try it yourself, then check the answer. So Ca plus O2 would give you CaO. I simply did the crisscross between calcium and oxygen, or you can do the charge balancing method. So this is one type I would expect you to predict. When you have a metal reacting with oxygen, you get the metal oxide, basically the metal combined with oxygen in a compound form. That's all that is. Sometimes you might see a non-metal reacting with oxygen. In cases like that, you could do the crisscross to determine what the formula would be, but it doesn't always work out. We don't always know. So for example, if I had C plus O2, that could make CO2. It could also make CO. It really depends on how much carbon and oxygen is present. It might make a bit of both. So the idea is that I want you to kind of be able to give a general guess of what they might come together to form, but in reality I'll probably just make you identify some like these. So if you have H2 plus O2, they come together to make water. That's one thing. That's a synthesis reaction. Another type that's very similar to so this one here, don't worry about predicting so much, just worry about identifying. Another type that I do want you to know how to predict, so one I want you to know how to predict is 3. I want you to know how to predict 3. So you have a metal and a non-metal coming together to form a compound. And basically all you do to figure out the product is you do the crisscross between the 2 elements. So here we have Na plus Cl2. You do a crisscross between sodium and chlorine, and you get sodium chloride. So for example, if I want to do, let's say, Al plus S8, I'll leave the K plus I2 for you to do, but Al plus S8, you simply do the crisscross between aluminum and sulfur, and then you get Al2S3. I know the subscripts don't match, but that's okay. What you would do after is you would balance the equation. So the subscripts are determined by crisscross, but then afterwards you could go and try to balance the equation out by changing the coefficients in the front. So right now I have skeleton equations here, but you could figure it out by changing the coefficients in the front. So I'd like you to try the k plus I2. So pause the video, try it yourself, and then see if you get the correct answer, which would be ki. I simply do the crisscross between k and I. So case number 1, you should know how to predict. Case number 3, you should know how to predict. Make a reasonable guess for case 2, but chances are, again, I would just give you it as a form of identification. So could you tell me that it's a synthesis reaction and why? There's a few other cases. So we have non-metal and non-metal. You could do a crisscross, but again, many possibilities could exist. For case number 4, I would really just give you an identification to do. So you'd have to tell me, oh, that's a synthesis reaction because we have two things coming together to make one. So for example, this might make some oxygen dichloride. You could do crisscross to determine it, but it might vary depending on how much oxygen there is and how much chlorine there is. Another type of synthesis reaction, and this is just one I'd expect you to be able to identify, not necessarily predict, is when you have a non-metal oxide. When I say non-metal oxide, it means a non-metal compound with a non-metal and oxygen in it, reacting with water, that actually forms an acid. And so the trick to making the product here would be you simply make a polyatomic ion by looking at what the compound is here. Here's a non-metal oxide. Taking the oxygen from water, adding it to the non-metal oxide, and that makes NO3. That's the polyatomic ion NO3. That's what you're going to make the acid with. You're going to have H, NO3, AQ, nitric acid. Just like that. So for something like this, I'd want you to be able to tell me that it's synthesis, but I wouldn't expect too much of a prediction. But it does make an acid, so nitric acid. This one here, you could probably try it yourself based on the logic we did here. We have CO2, put the O there, that's CO3, that's carbonate. So you're going to make the polyatomic ion carbonate. You're going to use the polyatomic ion carbonate to make your acid. So that will give us H2CO3, AQ. So that's carbonic acid right there. And again, you can see it's synthesis because there's two things coming together to make one thing. This is another scenario where you have, rather than a non-metal oxide, a metal oxide reacting with water. When a metal oxide reacts with water, it produces a base. And the way you figure out the formula is simply doing a crisscross between the metal and hydroxide. So over here we did a crisscross between calcium and the hydroxide ion. The hydroxide ion, remember, is HOH minus. So if I want to figure out the product for something like this here, I'd simply do the crisscross between the metal involved in the metal oxide. So we have aluminum plus 3, and I'm doing the crisscross with hydroxide, which is OH minus 1. And I'm going to put the hydroxide in brackets, crisscross it, and you get Al OH3. So metal oxide and water produce a base. These I'm most likely going to get you to identify as opposed to predict, but you should know how to predict them based on just reading this set of instructions. In grade 11, you'll have to know how to predict these for sure. So if you have more time, you can practice these to your heart desires. But at the moment, you just really need to identify them. So two things coming together to make one. You can try doing this problem here. Pause the video, try it yourself. And if you did it correctly, you would do a crisscross between potassium and hydroxide. And you get KOH, AQ. Another type of synthesis reaction is when you have a metal oxide, so a metal oxygen compound, reacting with carbon dioxide. To predict the product there, you simply do a crisscross between the metal and the carbonate ion. So your goal is to basically identify which case you're dealing with and remember what you're crisscrossing with. That's all it really is. So if you want to find, let's say for example, the product of the reaction calcium oxide plus CO2, you would do a crisscross between Ca plus 2 and CO3 2 minus, and that would give you Ca CO3. And you would do the same for the other ones down there. So you can pause the video, try it out yourself, see if you get the same answer. So I'm going to do the magnesium oxide plus carbon dioxide. Check if you got magnesium carbonate, MgCO3. I did a crisscross between magnesium and carbonate. And you can try this one out here. Now, some students might get confused and think, well, which copper do I use, copper 1 or copper 2? Well, you figure out which copper you have in this compound here. So in this compound, it's copper 2. When you do a crisscross between copper 2 and carbonate, you get CuCO3. Again, for this one here, I'm just going to get you to really identify that it's a synthesis reaction, because there's two things coming together to make one thing. Synthesis reaction. Now we're going to do the opposite. The opposite of a synthesis reaction is called a decomposition. Basically, one thing breaks down into many things. Okay, so the general equation for it is AB breaks down to produce A plus B. So one thing becomes two things, it could be three things, doesn't really matter. So this is one that I would expect you to be able to predict. If you have a metal oxide, it becomes just the metal plus O2. So for example, when I'm breaking this down, this would become lithium, which is the metal. And usually the metal is going to be in its solid form, plus some O2 gas. I know it's not balanced, but you could balance it using the coefficients afterwards. So pause the video and try this one here. CaO will break down, will decompose to form Ca, solid, plus O2. Gas. Over here is another one I would expect you to do on your own. So when you have a non-metal oxide, it will break down to form the non-metal and oxygen. So if you have CO2 breaking down, it would break down to form C plus O2 gas. You just have to remember the Hofbrinkel and the PS elements to represent them appropriately. Otherwise, you will lose marks. So try these ones out here. Pause the video and then see if your answers match. So over here I would have S8, sulfur solid, plus O2. And make sure it's gas. Over here I would have Cl2, and you know that's gas. Plus O2. Gas. So decomposition is a lot simpler than synthesis, but they really are just the opposite of each other. If you have a binary ionic compound, so a metal and non-metal, it'll break down to form the metal and then the non-metal. If it's a Hofbrinkel, make sure you put the 2 in the state as you would normally do. So for example, if you had ZnCl2 breaking down, it would simply become zinc, and usually the metal that forms is solid, plus Cl2. And you know it's Hofbrinkel, so it would be a gas. Pause the video, try magnesium chloride breaking down, and you should get Mg solid plus Cl2 gas. So what I would do if I were you is keep trying these until your answers match mine. Just follow the model that I do. Don't invent any other rules. Do exactly as I say in these examples, and you should be able to do any other example that arises. Same idea here. If you have a binary covalent compound, just two different nonmetals, you break it down into its elements and make sure you follow the PS rules and the Hofbrinkel rule. So for example, Hi would break down to form H2 gas. Plus iodine solid, so I2 solid. Pause the video and try the HCl. If you did it correctly, your answer should match mine. H2 gas plus Cl2 gas. For the last three that I'll be doing, 3, 4, and 5, I would expect to be able to identify that it's a decomposition. I don't really care too much about the prediction for these last ones, but it would not hurt to practice. If you have an acid, it will break down into water and then some binary covalent compound, usually a non-metal oxide. And so the way it works is like this. So if you look over here, you have H2CO3. And so what I do is I take out H2O first. So if I look at H2CO3, I actually take out water. I take out the equivalent of what would be in water. So that would be 2 H's. So H2. And then 1 oxygen. So that would leave 2 oxygens there. So that would be H2O. And whatever's left over is the non-metal oxide that would be there. So plus CO2. And you would know it's a decomposition because you have one thing, it becomes more than one thing. So this acid over here doesn't have AQ written next to it, it should. It breaks down to form H2O plus CO2. If you have a base, that will break down to form the metal oxide and water. It's actually pretty straightforward. So you would always write down water. It doesn't really matter what order you write them down in. So water plus the crisscross between the metal in the base and oxygen. So you would have K plus O2 minus, and that gives you K2O, and usually it's in the form of a solid. You can attempt this one here, pause the video, try it out using the same format that I followed in the previous example. If you did it correctly, you would get H2O. And usually when you have H2O, it's in the form of a liquid here. I'm going to add that over here just for the sake of completeness. And your metal oxide would be calcium oxide, CaO, crisscross between calcium and oxygen. Just like that. Now, the last one is a metal carbonate decomposing. When a metal carbonate decomposes, a metal carbonate is just a metal with the carbonate ion. It'll form some carbon dioxide and the metal oxide. So in this case here we have calcium carbonate. One of the products will for sure be carbon dioxide, so CO2 gas. And the other product is going to be the crisscross between calcium and carbonate, so plus Ca plus 2, CO3 2 minus. If you do charge balancing or crisscross, you would end up with Ca, should be oxygen, not carbonate. Let's redo that there. Let me erase that. So it's the crisscross between the metal and oxygen. So the metal over here is calcium. The oxygen is minus 2. If you crisscross it or charge balance it, you get CaO. So you get the metal oxide and some carbon dioxide. And usually the metal oxide will be in the form of a solid. You can do the same thing for the problem just below. So pause the video, try it out yourself. You'll notice that the copper you had in this compound is copper 2. So you would have CO2 produced and copper 2 oxide, CuO. So I would expect you to be able to identify this as a decomposition reaction. From this slide, the main one I would expect you to be able to predict is number 2. Number 3, 4, and 5, you should be able to identify them as being decomposition and why they're decomposition reactions. So this brings us to our last reaction in this PowerPoint. It's a combustion reaction, which basically means burning something in the presence of oxygen. And there's two types of combustion reactions we're going to see. There's something called a complete combustion reaction, and the other one is called an incomplete combustion reaction. And so usually what you do is you burn a fuel, usually called a hydrocarbon. The hydrocarbon is a compound that contains C and H, and then sometimes some other elements like oxygen, for example. And so over here is an example of a hydrocarbon, methane. Methane's a hydrocarbon, has C and H. Some other compounds are they're derivatives of hydrocarbons, like alcohols. They can also be used as fuels. And so what you'll notice is that the combustion reaction, at least for complete combustion, has the same general formula. You write down your fuel, which is your hydrocarbon, plus O2 gas. It'll produce CO2 plus H2O, all in gas form, plus energy. So it releases lots of energy, like an explosion almost. You'll feel some heat. So in this case here, we have CH4 plus O2. All you really have to remember that is if it's a complete combustion, it'll form some CO2 plus H2O plus energy. And it doesn't really matter what that hydrocarbon is. It'll always form the same two products. Now we call this a complete combustion because there's a lot of oxygen reacting. A complete combustion is a combustion reaction where there's sufficient oxygen, that has enough oxygen for a complete combustion to occur. Usually when you have complete combustion, you're going to see blue flames. So like when you see the Bunsen burner sometimes, you see that blue fire, there's lots of oxygen reacting to do a nice clean burn, and you see nice blue flames. And then all that would be left for you to do is to balance the equation if you needed to. So you could balance the equation by counting your number of carbons in this case. So we have 4 carbons on the reactant side, so we'll put 4 on the product side. In terms of the H's, we have 10 on the reactant side. So to get 10 on the product side, we have to put a 5 here. That leaves us with 8 plus 5. That will be 13 oxygens on this side here. Now with 13 oxygens, that's a bit difficult to balance here. So what we could do is, to get 13 oxygens, we have to do 6.5. Because if you do 6.5 times 2, that gives you 13. But remember, we don't want to keep the fraction, so we multiply everything by 2 in the end. And that'll give us 2 over here. That'll give us 13 over here. That'll give us 8 over here. That'll give us 10 over here. So now we have 26 oxygens on the product side, 26 on the reactant side. We have 20 hydrogens on the reactant side, 20 hydrogens on the product side. We have 8 carbons on the reactant side, 8 carbons on the product side. So this is one of those more difficult ones to balance, but if you get used to this trick, it'll be more straightforward. So again, any complete combustion reaction that you see will simply produce carbon dioxide gas and some water, and we're going to add energy. Because energy is released during these reactions, it's often explosive, or you can feel heat. So for example, if you're using a lighter, you're burning one of these fuels, one of these hydrocarbons, and it releases heat or energy, and we can see fire as a result of it. So these combustion reactions, these complete combustion reactions, they're exothermic. When we say exothermic, what that means is there's a release of energy. A release of energy. So think exo, exit, energy exits. So a combustion reaction is an exothermic type of reaction because it releases energy. A reaction that would absorb energy, that sucks energy away from you, that would be endothermic. So if there was an endothermic reaction happening, it would feel really cold to you because it's taking the energy away from you. It's taking heat away from you, so it would feel cold. So it's called endothermic if it takes energy away. The exothermic reaction, when you write it out, usually energy is a product. Energy is a product because it's being released. Energy is a product, like we see in the case of the combustion reaction. Energy is a product. In the endothermic reaction, because energy is being absorbed by the reactants, by the reaction overall, the energy would actually be a reactant. So energy is reactant. We don't see that in the combustion reaction, but we can in other reactions. So the other type of combustion reaction that we're going to see is called an incomplete combustion. So for the incomplete combustion, you still have a hydrocarbon, and it's still reacting with oxygen. It's just that now you have insufficient oxygen being used. It's an incomplete burn because you have insufficient oxygen. Okay. So when you see that keyword insufficient oxygen, then you know you have an incomplete combustion. Usually with incomplete combustions, you'll see the orange flames rather than the blue flames. And you'll often see this black substance that forms, this black powder. That's called soot. That's some of the carbon that's actually produced. It's more of a dirty burn, we say, because of that black soot that's produced. So in the case of an incomplete combustion, you still have CO2 produced, just like you had in complete combustion. CO2 gas. You have some water produced still, H2O gas. But in addition to those products, you now have some carbon monoxide produced. That's that silent killer. It's the compound that will bind to your red blood cells and prevent oxygen from binding. And so people, if there's a carbon monoxide leak in their homes and they don't have a carbon monoxide detector, they'll often pass away as a result of that due to carbon monoxide poisoning. And you don't know what's happening because you can't smell the gas. It's odorless, it's colorless, you can't see it. So that's why we often call it the silent killer. So there's carbon monoxide there and also some carbon produced. So whenever I say there's an incomplete combustion, you just put down these four products plus some energy because it's also exothermic. It releases energy. It's just that now you have the carbon and the carbon monoxide there. And this carbon is what is the soot. So it doesn't matter which hydrocarbon is here. If I said it was an incomplete combustion, you have to put CO2 plus H2O plus CO plus C plus energy. If it was a complete combustion, you'd simply put CO2 plus H2O. And basically, it's up to you to be able to balance the reaction afterwards, balance the equation. So, as I mentioned, if you have a hydrocarbon or some kind of hydrocarbon-like compound, so a fuel source, it could undergo a combustion reaction, and that releases lots of energy to the point where you could have an explosion. So, in this slide, I've included a link to a video at a sugar silo. Basically a sugar factory, where there was an explosion because of sugar. Sugar is a fuel. There was a lot of sugar dust in the air, a spark went off, and because there was oxygen present and the sugar dust was nice and spread out, there was an explosion in one area, and then that explosion fed other areas where there was sugar spread out, and eventually the whole sugar silo crumbled, and there were many deaths as a result of that. So I'll give you a hint here. The flames that were produced were orange. Knowing that the flames produced were orange, what type of combustion occurred? And once you answer that question, what I want you to do is write down the products of that type of combustion. You'll notice over here, this is sort of the ingredients you need for an explosion or a fire to occur. You need a fuel, which was a sugar. You need some oxygen from the air, so that was present in the sugar factory. You need an ignition source, and that was basically the spark provided. In the case of the sugar, if you tried to light a pile of sugar up, it wouldn't light up very well because there's not enough surface area for reaction to happen. But when it's spread out all over the air, there's more surface area for the sugar particles to react with the oxygen, and that can lead to a reaction. And then the fifth ingredient here was this confinement. So because there was so much sugar in a small area, that led to an explosion, and that triggered other explosions. So because all these 5 components were present, the sugar silo exploded due to the combustion of sugar. So you should pause the video and try to answer this question. I will give you the answer and you verify. So this here is sucrose, that's table sugar, the stuff that you put in your coffee. I said there were orange flames, so because there are orange flames, you know that we have an incomplete combustion reaction, which means there's some CO2 gas. There's some water vapor. There's some carbon monoxide. And there's some soot or carbon, which is solid, as well as energy being released because it's an exothermic reaction. And again, this is an incomplete combustion reaction. As part of your homework, you can attempt these practice problems here from one of your textbooks. There will be some worksheets that are posted online and also handed out in class, and you can attempt those. You want to be able to identify the different types of reactions as being either synthesis, decomposition, or combustion, and if they're combustion, can you identify them as being incomplete or complete? You should be able to predict certain products based on the ones that we focused on in this presentation, certain types of synthesis, certain types of decomposition. And for the ones I didn't really expect you to predict, you should still be able to explain why they are synthesis or decomposition. And for combustion, you should be able to write down the products and reactants of both the complete and the incomplete type of combustion, as well as provide certain characteristics of how you could figure out if something was a complete or incomplete combustion. In addition, I'd like you to determine what type of reaction is shown in this picture over here, and then I want you to modify the picture afterwards to make the other type of reaction that it's not. I'll give you a hint. I'm talking about 2 reactions that are really kind of the opposite of each other. And if you can come up with what type of reaction this is, then you're a true anime fan. And if you can modify it to make it the opposite type of reaction, it's even better.